Okay, so I'm going to start here with an example of the average rate of change. All right, so let's talk about average rate of change. And I'm going to use this as an opportunity to introduce a couple new ideas. I seem to have lost a rate of change. Okay, so here it is. Let's look at this example. Yeah, absolutely. So example, I'll do that in just a second here. Find average rate of change for f of x equal to 9 minus x squared. And I'll give us two parts. I'll say part A. Let me say part one. Part one we'll do from A equals minus 3 to A equals to, let's say, minus 1. And part two we'll do, say, from A equals, that was supposed to be a B. From A equals to 0 to, let's say, B equals to 2. And yes, good question. What was the average rate of change? So that's delta y over delta x. And so that's going to be f of b minus f of a over b minus a. This right here is the average rate of change from x equals a to x equals to b, all right? And we're going to assume that a is less than b here. All right? Okay, so, and then I'm also going to graph the meaning of what we're doing, okay? So let's work on it here. So number one. So we're going to go a equals minus 3 to b equals to minus 1. So we're going to calculate delta y over delta x, which in this case is f of minus 1 minus f of minus 3 divided by minus 3 minus a minus 1. Excuse me, is that right? When you're doing the average rate of change, like the values should sort of match up in the formula, right? It goes b then a and b then a, right? Notice I've got the b and then the a on the top, but in the denominator I flipped it, right? This is wrong. So I need to do what? Minus 1 minus a minus 3, right? And so what does that give me? 9 minus minus 1 squared minus, and I'm going to put some parentheses. Parentheses are your friends here. Parentheses are always your friends, but they're especially your friends here. What does the denominator work out to? I heard a positive 2. I'll buy that. And so can you guys clean up the numerator for me here? What happens? Can you see what cancels? I mean, you could look at it different ways, right? Like there's different ways you could see 9 canceling, right? This minus 3 squared is what? It's 9, right? So inside this, we're looking at 9 minus 9. So the thing inside the parentheses is just 0. So like f of minus 3 is 0 here. By the way, is that surprising? Let's graph y equals f of x equals x squared minus 9, which is what? X plus 3 times x minus 3, right? Oh, my bad. Ah, curses. Thank you. Thank you for keeping me honest. I appreciate that. Let's see here. 9 minus x squared. And thank you for pointing that out now, as opposed to 3 minutes from now. That's right. So it's 3 plus x times 3 minus x. But the point is, when you factor it completely, you can see that this function has x-intercepts at plus and minus 3, right? And in fact, we can graph this thing. Not quite to scale, I guess. Well, let me try to do it to scale. This is going to be 9, 6, 3. Well, sometimes it's just better to not work with the same scale on the, you know, the horizontal and the vertical. It's probably the case here. So if this is minus 3, and this is 3, and this is 9 up here, something like that, right? It's a parabola which opens down. And what we're just calculating here is that minus 1, right? What's f of minus 1? What is this value? F of minus 1 is actually what? It's actually 8, right? F of minus 1 is 8. So this point right here is at 8. And then, of course, this point up here at the top is where? 0, 9. Now, I'm sorry, why am I talking about that? We're not to that part yet. What are we doing here? We're doing minus 3 and minus 1, right? So where's minus 3 in this picture? That's this guy over here, right? Okay, so what did we figure out the average rate of change was actually? What's this? This is 8 over 2, right? So the average rate of change was, did I hear 4? Yeah. So geometrically what that means is that if you look at the line which connects the point at minus 1 to the point at minus 3 on the graph, it's got a slope of 4. So like that line is this one. That was supposed to be a line. Sorry. So this guy has delta y over delta x equals to 4. It's got a slope of 4. All right. Part 2, we're going from a equals to 0 to b equals to 2. We calculate the change in y over the change in x, calculate the average rate of change. So we've got f of 2 minus f of 0 over 2 minus 0. But what's f of 2? It's 9 minus 2 squared, right? Minus f of 0, which is 9 minus 0 squared, all divided by 2. So what's that work out to? The 9's cancel this time, right? So this 9 cancels that 9. And we're just left with what? 4 over 2, but there's a minus, right? So we get a, looks like a minus 2. So what's going on there? Well, we're thinking about going from 0, which is this point up here, right, over to 2, which in my picture is like something like that, right? And so if you look at this line that connects those, right, the slope of this is minus 2, right? Now, of course, the slopes are not what we're used to because my scale on the vertical axis and my scale on the horizontal axis is not the same, right? So, you know, our slope 1 doesn't have 45-degree kind of angle like it would usually if we do the same scaling on both of the axes. So, but you can still see that this is a more shallow slope than that one, even with my limited picture. Okay, so let me introduce some terms. So what do we call this point at the top of the graph? This is called a local maximum, right? Or you can say, actually, in this case, it's a global maximum because that point right there is the biggest that the graph gets anywhere, right? But a local maximum is when we've got like a place in the graph where if you're close to there, there's no other points which are above it, right? This is the idea of a local maximum. So that's a local maximum. Another thing I can tell you about this graph is that this function is increasing, right? The function's increasing one place and it's decreasing another place. What do we mean by increasing? We mean that as you look at the graph and you go left to right, if you're increasing, you're like going up the hill, right? And then if you're decreasing, you're going down the hill. But it's important that we go left to right, all right? Otherwise, it gets backwards. But you notice that if the average rate of change between successive points in an interval is positive, that suggests that the function's what? Increasing, right? On over here, the average rate of change between successive points to the right of the y-intercept is negative because the function's decreasing over there. So we can see there's a connection between the average change idea and whether or not functions are increasing or decreasing, right? Now, for the sake of logical completeness, I should give you a definition of increasing. F is increasing on, let's say, I, a subset of the reals, if A, B in I with A less than B implies f of A is less than or equal to f of B. Right? So that's f is increasing. F is decreasing on I. So what is I? That's a good question. I is a subset of the real numbers. So when we talk about increasing or decreasing, it's a property that a function has for not just one point, it's a property that the function has for like a set of points. All right? So I could be like the open interval from 0 to 1. It could be the whole real line. I could be a closed interval from -2 to 3. You know, it could be any of those intervals we talked about in the first class. So I use I for interval. Usually we talk about increase and decrease on an interval. In principle, you could talk about I being like a union of two disjoint intervals if you wanted. But when you start looking at that, you get kind of weird things. F is decreasing on I, a subset of R, if AB in I with A less than B implies that f of A is greater than or equal to f of B. And that has to be true for all possible pairs in the set I for it to be increasing. So I'll ask you guys the same question I asked the other section. What would happen if a function is both increasing and decreasing with this definition? What would that say about the function? It's got a turning point. Well, you know, I would say that's not a bad idea. I would say that if it's both increasing and decreasing, you could justifiably say that every point's a turning point. That's kind of true. I mean, you're right. In this one, between where it's increasing and where it's decreasing, there's a turning point, and that's the local maximum. Right. There's a gap in the graph. No, well, let's just, here, let me be more low-tech about it. Suppose we have two things at once. We know that this is true, and we know that that is true for arbitrary A and B in the set. What would that tell you about f of A and f of B? what happens if f of a is less than or equal to f of b and f of a is greater than or equal to f of b? That means it's equal to. And so what does it mean if the function's equal to, f of a is equal to f of b for every a and b in the interval? It's a very boring function, right? Whatever value it is, right? It's a constant function. So a function which is both increasing and decreasing on an interval is a constant function. So constant functions are kind of like in between these two worlds of increasing and decreasing functions. Okay. So I just wanted to use the average rate of change idea as an excuse to introduce some of these terms to you. Now we're going to play a game. The game is going to be, is this a function? Is this a function game? Can I erase? You're confused. I don't remember that name in the roster. I'm sorry, that's horrible. I'm a dad. This is the kind of jokes we make. Yes, what were you asking me? Oh, that is a good question. We are going to get back to graphing. That's all we're doing after we get done with this game. So just hang right in there. I agree. We need to spend a lot more time about how we graph. That is one of my goals today. What's that? Hangman? No. Are we good? We've got all the pictures we need? I can erase? Okay, cool. So, here's the question. I mean, here's the game, basically. Is this a function? That's the game. Is it? I mean, I hope you take notes. But so, example 1. So suppose you're given that the graph of some equation, right? It looks like this, right? So here's y, here's x, like that. Is this the graph? I should say more specifically, is this a function, or is this the graph of a function? And why not? Does not pass that line test. Which line test? Oh, I could pass the, look over here, this one passes the x-axis twice.
Not the x-axis, but it can't go, you can't have 2 values for x.
2 values for, right, you can't have 2 outputs for 1 input, right? Like the same so that you're right, it's that test. This is the vertical line test, right? Fails vertical line test. So no. Right. Another one. We could have a function that looks like this. Oh, excuse me. Dang it. Forget I said that. Is this a function? Hey, you guys are cheating with my answer. I did it. That's true. It's all my bad. All right, so is this the graph of a function?
Yeah.
Yes. This would be an example of a piecewise defined function, right? We've got like a different shape for different pieces. Actually, this is, I mean, piecewise, I would actually have to give you formulas typically. Well, I'll do that next. Well, actually, that doesn't fit this game. I'll have to come back to piecewise later. Okay.
Can you explain what is it?
Oh, sure. Because, so remember the critical thing about a function is that if we put an input, let's say that this is 4, right? Then this point right here is 4 comma f of 4. That's what it means to be in the graph, right? If it's on the graph, we have y equals to f of x. But this point up here would also be the point 4 comma f of 4, right? But that y value and that y value are different. That would mean that f of 4 has to be both of those things. But that's not allowed. A function has to have a single output. So that's the vertical line test. If you can cross through the graph of an equation more than once, It's not the graph of a function. Now be careful, vertical line, right? There is a horizontal line test that we'll talk about towards the end of chapter. That has to do with what's called the one-to-one function. We'll hopefully get to that Tuesday. But this is a function because any vertical line you can think about, right? Doesn't matter which one. It only crosses through the graph of the function just once. There's a unique y value assigned to each x input in the domain, right? Now, if I told you that this was minus 5 and x, and this was 1, and this was 2, and this over here was 8, well, maybe 6. Maybe 6. Can you tell me what's the domain? And this is y equals f of x. Tell me what the domain of f is. An interval notation. I'll get us started. Minus 5, not included. And then unioned with something else. Help me out. Minus 5 goes to where? All the way over to 1. Again, it's not included because of the circle. And then we union with what? 2, which is included. So I got to do the square bracket. And 6, and is 6 included? It is, so I got to do that square bracket. I'm okay. It's the COVID, you know. Got to watch out for the COVID. If I'm breathing up here, it's safe for you. If I'm breathing over there, it's not safe. Hey, them's the rules. I didn't make them up. So I try to keep my mask on or hold my breath if I'm moving around class, right? Anyway. Okay, so we can play this game all day long, right? I give you a picture. You see, does it pass the vertical line test, right? You can decide whether or not it's a function. But there's another kind of example where, and these problems are in section 2.3 in the recommended homework. There's like a bunch of them. And the other kind of problem you can ask is, you know, maybe you're not given a picture. Maybe you're given an equation. And you have to decide whether or not it's a function, right? So here's the one. X squared plus 4x squared plus y squared equals to 0, right? So there's two ways we could decide whether or not this is a function, whether or not the graph of this equation corresponds to the graph of a function, right? The two ways we can go is one is to graph it. The other is to use algebra. I'm going to start by graphing it, which also requires algebra, actually. Everything's algebra. So how did we look at this before? We did what? We complete the square, right? So this gives us x plus 2 So once I put the thing in standard form, you can see, hey, this is actually a what? What are we looking at here? A lot of you guys did this on the test pretty well. You not included? Don't be like that. So this one is a circle, right? This is a circle. At minus 2, 0. What's the radius? 2. See? There's hope. All right, so here's a picture you just cast. Well, don't tell me that. So it's a circle at 2. If I was smarter, I would have drawn the circle first and the axis second, but oh well. So a circle with radius 2 centered at minus 2, 0. That's what it looks like. Is it? So is this the graph of a function? No, right? Nope, not the graph of a function. Fails vertical line test, right? Now, let's look at how we would do this using algebra. So the way you test if an equation is in fact the graph of a function in disguise is you simply, what's the algebraic method? Simply try to solve for y. So we've okay, that's fine, that's fine. And in fact, for the record, you do not have to ask me if you need to go to the bathroom. Like I have my 101 classes, a lot of them are asking me if they need to go to the bathroom. I'm like, I mean, that's for you to know, you know. I mean, I don't know. But anyway, okay, so can we solve this for y? What happens? Isolate y squared equals to minus x squared. Oh man, you guys should have stopped me. I wrote something down wrong and I just went on. And if you're confused because of this, you should be, because I made a typo in the problem statement. But yeah, this is, that is not supposed to be there. You guys got to speak up. Yeah?
I mean, I seen it. I just thought
You seen it? You just ignored it? No. Well, I did combine it. I complete the square, right? X plus 2 squared. That's the least of your worries. You knew what I meant. So we have two classes of spectators. Spectators. What is wrong with me? Spectators. I need a nap. Ooh, that is tempting. That's tempting. But no. So we complete the square by taking half of that, x plus 2 squared, and then of course that adds 4. So I have to subtract 4 to be fair. You know, it adds 0, and then the y squared just rides along. So. Sorry about that. So if we just solve for y squared, we've got y squared is minus x squared minus 4x, right? Which we could rewrite as y squared equals to minus x times x minus 4, x plus 4, right? Now, all right, this gives me a little bit of cause for concern. We've got something squared equals to something that looks like it might be negative. But is that a legitimate comment? Is that negative? Like how do you decide whether or not minus x times x plus 4 is negative or not? Set it equal to 0. Well, that's the right kind of idea. If we set it equal to 0, that tells us that the places where it could be 0 is 0 and minus 4, right? 0 and minus 4 are the places where the sign of this can change from positive to negative. So we can make a sign chart like we learned, right? And we can put minus 4 here, we can put 0 here, and we can plug in some points. Like what happens when you plug in 1? 1 times 5, we get a minus 5, right? So this expression is negative over here. It's negative over here as well, and it's positive in the middle. So if we're going to solve the equation above, the only place where we can reasonably solve the equation above and hope that the solution is real is when x fits into this positive region, well, or the edges, right? So what I'm trying to say is, for minus 4 less than or equal to x less than or equal to 0, we can take the square root. Right? And when we do that, we get y equals to plus or minus the square root of minus x times x plus 4. Now, guys, full disclosure, when I first did this problem, I didn't think about that sign chart thing I just did. I just went ahead and I took the square root, I wrote plus or minus, and I was like, that's the solution. And then I started thinking about my life. Did what I just do make sense? Can I take the square root of that equation? Is that a reasonable thing to do? And the answer is sometimes. Sometimes it's reasonable. But if you look at it, look at the graph we already have, it makes a lot of sense why we were driven to that range of x, right? Because this over here is minus 4, and this is 0. So it's just between here and here that the algebra comes together. So, okay, great. From an algebraic perspective, why is this not a function then? What's the problem? I see 2. 2 outputs for the input, right? That plus minus, game over. That's 2 answers for 1x, plus and minus, right? Now, if we choose just one of those, or just the other, we've got a function. What does choosing the plus correspond to graphically? The top part, right? So the top, this guy, is y equals to the square root of minus x times x plus 4. And the bottom part, soon to be drawn in, well, black, I guess. Come on. This guy down here, that is y equals to minus the square root of minus x times x plus 4. So, a circle, it's not far from being the graph of a function. It's actually the graph of what? Of 2 functions just pasted together, right? If you look at the vertical line test, notice that it's okay for like the upper half circle or the lower half circle, right? A vertical line only cuts through the green line just once. It only cuts through the, the black curve down here just once, any vertical line. So, hey, listen, let's do one more example that's easier to try to drive this algebra method home. Suppose y to the 4th equals to x. Is this the graph of a function? Now, how could you do it? How could you do it? You could make a table of values if you wanted, But what I would do here would be to try to solve for y. What happens when you try to solve for y? You get plus or minus the 4th root of x. So you may have forgotten about this, but in the earlier sections or from your previous course, you should have learned that when you take like an odd root, so if I have like y cubed equals to stuff, then the solution to that is just y equals the cube root of stuff. However, if you have y to any even power equals stuff, then the solution is y equals to the even power root. Let me come up with a name for this. Let me call this power 2j. So you take the 2jth root of the stuff, and that's the solution. But the thing is, you get plus or minus with the even case. So plus or minus, therefore, not a what? Not a function. The other way to solve this graphically, you just got to use your imagination a little bit, right? So I think that's worth talking about for just a second here. So we talked about last time, this is y equals x to the 4th, right? So what does that mean x equals y to the 4th looks like? You have to switch the roles of x and y, right? So basically you just take this graph and you turn it on its side, instead of opening up, it opens right. So it's like this. And so, yeah, vertical line test, fail. And as you can see, it fails it by hitting it twice, just like we found with the algebra. Okay, enough of this, enough of this. It is now time to talk about another game. So here we have case 1, y equals x cubed. Case 2, y equals x squared. Case 3, y equals 1 over x. And case 4, y equals the absolute value of x. All right. And then here's the, here we go. So let's call this A, B, C, D. So, assuming those are x, y axes, right? Tell me which goes with which.
A goes with 3.
I heard. Here, I'll tell you what, I'm going to write the answers over here in red. So A is 4, right? This is the what?
B is 2.
That's the absolute value function, right? The graph of
B is 2.
B is 2. C is 1. Yep. D. All right. Great. That's what I was trying to get. That's the skill I was trying to get across to you, giving you that list of examples last time. That's the kind of matching you should be able to do. All right? We can have that. Yeah, I mean, that should be part of the test, actually. But it's not just that. It's that wrapped together with what I'm about to show you. Oh, there's always a string attached, you say. I mean, you can put your name on the test. Yes, I do not. I mean, of course. I do like names to be on tests, but it's hard for me to give credit without that. That's definitely true. Were you going to put somebody else's name on your test? Yeah. You guys are funny. All right. Hey. Uh-oh. So there. Now they can see what we're doing. So we should talk about how to create new graphs from old. All right? So there's just a few basic operations we have, all right? So let me start making a list here. Number 1, we can take y equals f of x. And actually, each one of these, let me just say, begin with y equals f of x, then number 1, g of x equals to f of x plus c. What does that look like? What happens? What does it mean if we add c to the constant? Add c to the formula. So what this does is it shifts vertically. By c. So let me give you an example of that over here. Example of 1. This is y equals x cubed plus 1. I took one of our match games, number 1, I shifted it up 1. That's it. So we can add 1 to move the graph up 1. It just moves all the y values up by that constant. If c is negative, it shifts it down, right? So c positive shifts up, c negative shifts down. Number 2, we could look at g of x equals to, let's say, f of x minus c. Then this shifts right by c. And I'll tell you what, for the sake of, I'm assuming c is positive for this discussion. Just for now, let's assume c is positive. We can think about what would happen if c was negative, If c was negative, it would change like upward. I should say upward then, upward by c. Sorry, guys. I have trouble making choices sometimes. It shifts upward by c. It shifts right by c. Right? If c was negative, instead of upward, it would be downward. Instead of right, it would be left.
Well, isn't it negative in 2?
No, c is positive. So let me give you an example of that. This would be y equals to absolute value of x minus 1. So you didn't see this in high school?
I had a coach for math
A, co-
all 4 years of high school.
a coach for math all 4 years?
We didn't do anything.
Like a life coach or like a coach?
Like the football coach.
Oh.
And history had baseball coach.
History had a baseball coach. Well, baseball is a rich and storied game, so that could work.
This one.
Who won the state?
That was in 70s. I don't.
I had a physics instructor who would ask us about like that week's science news as a bonus question, like which satellite got put into orbit this Friday. It's like, I don't know. I don't follow NASA. Not that following was something you could do back in 1996 when I took that class. But anyway, look. So if you don't believe me, think about this. What happens when you put an x equals to 1? Put x equal to 1 into here. 1 minus 1 is 0, right? So the x-intercept of this is indeed right there, right? So it's a little bit counterintuitive, but if you want to move things like horizontally, it's the opposite kind of thing. You have to put minus the shift, all right? So let me give you another example of that, just to try to drive the point home. What I'm saying then is if we take, think about f of x equals to x squared, and replace it with with g of x equal to x minus 2, my claim is that what that does is it shifts the graph right 2 units. And if you think about that, right, y equals x squared is this guy, right? Y equals, x minus 2 squared is over here, isn't it? Because it bounces off the x-axis at x equal to 2, right? So, I can't draw it worth anything, but those should be exactly the same shape, just shifted 2 units to the right. So, yeah, 3, if we let g of x equals to c times f of x, then this is going to be stretches vertically by scale factor c. If we do g of x equals to f of cx, then it shrinks horizontally. shrink's the right word? No, shrink is not the right word. I think I should say, not shrinks. What's the, oh goodness. Well, let's look at an example. We'll decide the right word. Yeah. So the 3 is easy enough, right? 3 is easy enough. The example of that. So if we had, like here is, if this is y equals 1 over x, what would y equals 2 over x look like? So like if this point is 1, 1, y equals 2 over x is what? 2, 1, right? So it's like up here. If we're out at 2, we're at a half. Y equals 2 over x is at 1. So it's basically just, I'm not doing it justice. It's twice as far down everywhere. This is. Let's see what happens when we take the function and put in a multiple times the argument. What does that do? Let's try something relatively interesting. So like f of x equals to, let's see here, how about x squared minus 4, right? That's what? That's x minus 2 times x plus 2, right? And so you're asking me about graphing. Like the first thing I do for graphing is I try to figure out where the x-intercepts and the y-intercepts are, right? And if I can do that, then I'll kind of go from there. This has a y-intercept of what? Minus 4. And it has x-intercepts of plus and minus 2, right? So y equals x squared minus 4 looks something like that. Now, let us do an experiment. Let's try replacing x with some multiple of x. Like, what do you want the multiple to be? How about, want to do 3 times? We could look at g of x equals to f of 3x. That would be what? 3x quantity what? Squared minus 4. That's why I was spending a lot of time last class on evaluation, right? It's something we have to keep doing. We evaluate functions at, values, but also the expressions, in this case 3x. And what happens here, this is 9, x squared minus 4. Can you factor that? That's how it factors. What are the x-intercepts to this one? No. Yeah, if you set this equal to 0, what do you get? Like 3x minus 2 equal to 0 gives us x equals to what? I got a 2/3 or minus 2/3, right? So where is that? If I draw that on the same graph, right? The original one, if I draw that up here to compare them, 2/3, that's, it's like, it's inside of 1. It's like over here, right? And so basically you're like, so is shrink the right word? Somebody said compress. I like that. Compresses. Graph horizontally. By C. So this one shrunk it horizontally by a factor of 3. So the point is, we have these different operations, these different operations we can do on the graph. There's a couple more, right? What else can we do? We could think about like kind of a special case. What happens in case, well, okay, so first of all, you can think about what happens when c is negative, right? When c is negative, we shift downward by c, we shift left. Like if we had x plus 3 here instead of x minus 3, we would go like 3 to the left. If you have negative constants here or here, it flips the graph over and stretches. Or it flips the graph horizontally and stretches. Let me look at more like simple case. So 5, g of x, this is easier to think about. Minus f of x versus 6, g of x equals to f of minus x. So like g of x equals to minus f of x, what's that do? That flips the graph over the x-axis. So flips over x-axis. And what is replacing x with minus x in the argument? That flips it over the y-axis, right? And that will quickly take us back to the ideas of even and odd functions, right? Like if we have that you know, in number 6, if we have that g of x is equal, if f of x is equal to minus f of x, then we say that the function's even, right? So an even function is one that when you flip it over the y-axis, it doesn't, you get the same graph again. Like these are even because if you flip these over the y-axis, you just get back the same graph again. Okay, so now that we have all the toys in front of us, let me look in your recommended homework. And, oh, by the way, page 166 is a really nice presentation of what I did at the end of last class. I'll leave it up here if you want to take a picture of it. If you don't have the book or whatever, feel free after class to take a picture of that. I mean, I think it's helpful. You don't have to take a picture right now, like later, but if you want. Yeah, page 166. So we're currently, guys, in section 2.6. And so these are the fundamental building blocks, but then what we like to do is to combine them and to try to think about looking at an equation and explaining how would you understand it. Like let's look at some of the recommended homework for a second here. All right. I'll do it over here. Can you thanks. So I'm going to write down this is number 29. So here we have f of x equals x squared plus 3. So starting one of your fundamental examples. Remember the fundamental examples I shared with you last time. It's those 10 basic example types. Linear, quadratic, cubic, reciprocal function, the absolute value function. Starting with one of those basic functions, how do you get this one? Like if we think about y equals f of x, this is what? We could say this. This is the y equals x squared graph. Shifted what? Shifted up by 3, right? So if we want to graph it, we just think about taking the y equals x squared graph, which I'll make dotted, and we just shift it up by 3. And that's how you can graph. You take your standard example we shared with you last time, and you move it around. Let's see here. How about this one was not a recommended homework problem, but it's even, so it's good for me to talk about it with you. F of x equals to the square root of x minus 4. So the basic graph I have in mind here is the square root function, right? What do we do to the square root function to get y equals f of x? what would this look like? Shift 4 which way? To the right. Right. So we shift right by 4. Let's see here. How about, let's look at number 46. I thought this particular stuff was so cool the first time I saw it because it just opened my eyes that once I understood, about 10 basic graphs, I could easily create a bunch of other ones without plotting points at all. I just know the basic example and I move it around. Follow these rules, It's really neat. Number 46, and this is from section 2.6, right? Number 46, we're given y equals the square root of x plus 4 minus 3. And number 48, we're given y equals to 2 minus the square root of x plus 1. So these are starting to get a little bit trickier. How are we going to do those? Left 4 and down 3. So you're saying you take y equals the square root of x, and you go left 4, which that takes us to y equals the square root of x plus 4, right? And then you go down 3. Yes. I have to be careful. Sometimes it matters which one you do first and which one you do second. This is especially true of number 3 and 4. Like if it's like the stretching or the compressing. If there's stretching, compressing, and shifting, like doing one then the other and the other then the one, it could the order matters. But this is fine. Like if it's just successive shifts, it actually doesn't matter which one you do. And so this one, I think, like some of you might have said, you go down 3 and then you shift left. Like we could have just as well said what? I mean, check this out. We could have just as well said down 3, right? That would have given us y equals the square root of x minus 3, right? And then we could have done what? Shift left 4. And they would get us to the same place. See, when you're just looking at horizontal and vertical shifts, it doesn't matter if you do the horizontal then the vertical, or if you do the vertical then the horizontal. You get to the same result. So that's kind of cool. And the same will be true for that one. It's not going to matter. Oh, wait a second here. Well, what else is going on here, though? If we start with y equals square root of x, how do we get to this? What do you want to do? See, if you tried to add 2, right? If you shift it up 2, then you get y equals the square root of x plus 2, right? And then you'd be in trouble because you need to get that minus, right? So that minus is pesky. We probably should go ahead and take care of that to start with, right? So I suggest what we do is we try to reflect across x-axis, right? That would get us to y equals minus the square root of x, right? And then we can do what? We